in a faculty in the Department of Applied Statistics. So I will discuss much more. So Nafsat has already been given an excellent introduction about the regression, and I will try to carry on the discussion with some more mathematical aspects and multiple regression, and I will then switch to the hands-on part. So let me just share my screen. Oh, sir, it is saying that I am not allowed to share my screen. So will you kindly allow me to share? Hello.
Sir. I'm taking, sir.
Yeah.
Now check, sir. Now, okay.
Yeah. Now I am. Yes. I hope my presentation is visible to all of you.
Yes, sir.
So I would like to thank the organizing committee, Meadow Agriculture, for this opportunity. So as regression suggests that we will basically we have the input and output variable that is been also designated by the name as predictor and response, and our target will be to fit a particular curve so that it can use for the prediction. Now, it is not necessary that the regression will be always linear, but our today's focus is mostly only on linear regression. So linear regression means we will try to fit one line based on the data set that we are available with. And we can also do some nonlinear regression where the curve, so the curve may be parabola, maybe ellipse, this kind of curves we can also fit. Basically, any polynomial also we can also fit so that those particular curves can be used for the predictive modeling. So this is one equation for the regression model. So this is written in the vector form that Sir has already presented. So this y is the response vector, and this x is the prediction vector. And there are other assumptions that will also need to be satisfied so that we can apply the linear regression. First and foremost assumption is the expectation. This is called the expectation, which is those who are not aware with the term expectation, you can also interpret it with the mean. So mean of the error term, this will be equal to 0. So this is quite intuitive because our expectation is the lines would be fitted through the data points that we have already presented. So if the data point are being fitted with the line, that means there are no chance of having errors. So that means our goal is in the least square error method that errors should be equal to 0. So that is why these assumptions should also be given in the regression model, that the error mean of the error should be equal to 0. And there is another assumption we should also maintain, that is a constant variance. So this is called homoscedasticity property, where the variance of the terms of the error terms should be always constant. So there would not be any bias of the model. So this correlation and regression relation, Sarah has explained. And these are, I will just recall the term, what it is being called. This is called a intercept term, this is called a slope term, and this epsilon I, EI, whatever you say. So these terms are actually the error terms that we need to model. So these are least square criteria Sarah has explained. So in that one, I will just try to define two quantities. One is called SSE. It is the full form is sum of square of error. So what is sum of square of error? Sum of square of error is this yi is the original predicted value, original response value, and this b0 plus b1 xi, this is called the predicted response value. So original minus predicted, if you take the square and if you take the sum, so this is sum of square of error terms. So that is why it has been defined as SSE. And for SSE term, I have just explained. So similarly, we can also define two other terms. One is called SST, that is called the sum of square of total. So total means we have to take the difference of the predicted response values with the mean of the response values. So yi minus y bar square. And this is called sum of square of regression, SSR. So this is basically, we will take the difference of the predicted value with the mean value. So with the mean line, if I consider, we are getting basically two extra terms which are called as SST and SSR. And there is a beautiful relation between these three sum of square terms, which is sum of square of total is basically nothing but SSR plus SSE. If you want to see it mathematically, it is not possible for this short span of time, but we can discuss it geometrically. So this is the average line that I am talking about. So these are the data points, and this is the best fitted line that I'm fitting with the data. Now, as we can see, this difference is basically the difference of the predicted data with the mean line. So y cap minus y bar is representing that. So this is the basically the value of SSR, and this is y minus y cap. That is the original minus predicted value. So that is SSE. So that means this, if you take this term SSE, and if you take this term SSR, so if you add them, so SSE plus SSR, which will give you the total error, which is known as SST. So that is how geometrically you can explain how this relation holds, SST equal to SSR plus SSE. Now this is a very key term, this is a very key relation to define something called R square. So R square is basically nothing but SSR by SST, but this is a very not a very good way of representing the coefficient. So we will use the relation SSR equal to SST minus SSE. So if we use that simple algebra, we will get 1 minus SSE by SST. Now this one will help you understand how the regression will be determined with the coefficient of determination R square. Now why this particular term is needed? I mean, if I just give you with a real life example, like if you go to suppose a grocery shop, there are lots of options available for say for the saving. You are buying a soap, so that means there are different brand soaps are available. So obviously you will try to buy one soap which is the low cost, having the low cost. That means you use it for the optimal number of days and optimal price. So our target is that. Yes, hello.
Well,
I request if there is any mic open, please mute that. Yeah. So, so our target is, if we have a lot of available options, we will try to always optimize that. So R square will help you to do that, because if we have a lot of data points like this, you can fit a lot of lines. We can draw any kind of line on this particular data points, but how we will determine that which line is the best fit? So to determine the best fit, we will use this quantity R square. So our best fit means there will be no error. So if there is no error, that means this SSE terms would be 0. So if you put a 0 here, what you are getting? R square equal to 1. So that means that is the best fit possible line. So if you can have a line where R square equal to 1, that means you are having the best fit line. But in reality, it is not possible to have R square equal to 1 because the data is not lying on a straight line always. So that means our best possible case would be the value of R square to be very close to 1, as much as possible to 1. As I has described in his example, the R square value was 0.92, which is a very excellent agreement with the regression. So our expectation would be R square value will be more than 0.8 at least, so that we can say this is a good fit and we can go with the model. If R square value is suppose less than 0.5 for the time, for the reality say it is the value is 0.3 or 0.4, that means the regression model is not working. That means the regression, maybe it is not a linear regression at all. You have to go to the nonlinear regression part. Otherwise, you can, if the R square value is good enough, you can go with the model. So R square is a basic indicator to show your model is working or not working. That we will also see in the hands-on part, where R programming will give you the value of R square. Okay. So now another two things that help you to determine whether the model is good or not. That is called MAC. That is the mean square error. and the mean square error is nothing but sum square of error that I've just explained, and divided by the degree of freedom of the term. So here the degree of freedom is n-2, so we are dividing that. So another concept is this that inference cross slope. So why it is required? Let me give you one simple example. Suppose the model depended on two inputs, or suppose a single input is only dependent. Say there is the yield and irrigation model that Sir was explaining, that in the irrigation model, the irrigation parameter, how do you know that the irrigation is dependent on the system or not? I mean, whatever irrigation model that you are fitting, whether it is dependent on the irrigation or not. So that means you have to do some statistical test to check whether the irrigation parameter statistically significant to the model. So to check the statistical significance, we will do something called hypothesis testing. So hypothesis testing, there is a null hypothesis that we have to assume. So the null hypothesis is the B1. So what is this beta 1? Beta 1 is the slope parameter. So in the regression, there are two parameters, y equal to a plus bx. So that a and b, whether they are dependent or not. So to show that in the null hypothesis, we will assume that a and b to be 0. Now we will use a t statistic, which is nothing but the sample value for the corresponding slope and the corresponding standard error AC. So we'll calculate that and we will check the p-value. So if the p-value is quite large, preferably more than 0.05, that means null hypothesis is not accepted. That means the statistical significance is there, because hypothesis saying beta 1 is significant. But if the p-value is very less, suppose it's 0.001, so this suggests that the model null hypothesis you cannot you have to you cannot reject. So that means beta 1 has to be equal to 0. That means the parameter is not significant to you. Okay. So these kind of things, that means whether the parameter is significant or not significant to the model, we can determine by watching the p-value, the corresponding p-value. So we'll discuss that also in the hands-on part. These are the assumptions. I've already talked about one assumption, that is the constant variance. The variance should be always constant. There are other assumptions as well. For linear regression, the normality of error should be held. That means if you are considering the error terms should always follow the normal distribution. So it can also be checked by doing the error plot, a simple histogram plot. And if the histogram is following a bell-shaped curve, that means the error is in the normal distribution. So that means you can apply the regression, simple regression, linear regression. For nonlinear regression, there is no such assumption. But for linear regression, you have to always follow the normal distribution. Otherwise, you have to force it to follow the normal. Otherwise, you cannot apply the simple regression. And how to check whether a given data set following normality or not. You can check from the homoscedasticity or heteroscedasticity plot. There is also given some indication, but the main indication is provided by the normal QQ plot. So this QQ plot, I will not go into the detail, but this is just a cross plot where original value and predicted value are being given. And if the value is lying on the 45-degree line, that means we are having a normal distribution. Now, in real life, the yield, suppose in the yield example, yield is depending on the irrigation, but maybe that is also dependent on other factors as well. Crop yield is also depending on how much sun exposure is there on the land, how much more fertilizer is given to the land. So there are other factors as well that we need to keep in mind. So if there are multiple factors which is affecting the crop yield, we cannot explain only a single variable. We have to introduce multiple variables to describe the crop yield, and that is why the multiple regression comes. So this is also a linear regression, but so here the number of inputs are much more. That means you are now not fitting a line, you are fitting a plane. So you are fitting a, how to say, it is a in n dimension you are fitting a hyperplane actually. So I'm not going to the mathematical details, but for 3 dimensions, say if there is x1 and x2 and y, 3 variables, so you are actually fitting a plane there. So multiple regression works like that. So for multiple regression, you cannot explain the regression by only only a single variable. We have to introduce multiple variables, and the number of variables are being denoted by P. So P is the number of inputs that we are using, and by using this rigorous calculation, we will get a similar form of least square method, but in the matrix form, which is given as this. And under the same assumptions, we will do the calculations as well, and we will get the same expressions. But if you remember, the MSC was SSE by n minus 2, because in the single regression case, there was only one predictor. So one predictor means P equal to 1. So that is why it is n minus 2. But if you have, suppose, say 5 predictors, 6 predictors, so you have to divide n minus 5 minus 1. That is how. So P is here an important factor we need to incorporate, because there are number of inputs are much more. The test statistic is same. We can also use it for checking whether one input is dependent on the parameter or not. Like here, the significant test will be much more important, because the crop yield example that I'm discussing, here irrigation is important, okay, but sun exposure, is it too much important for the model or not? So how to test that? So we will do the hypothesis testing to check whether the sunlight exposure is important or not. If it is having the p-value large enough or small enough, based on that we will decide whether we can incorporate that in the model or we can exclude that to the model. Another way we can check, this one I will just discuss briefly, that overall global significance. That means whether the parameters that we have introduced to the model, whether they are significant at all in global sense. So how to test that? We can test that by using F statistic. So this is F statistic, which is MSR by MSC, and the expressions we have already discussed. So if the value is quite say, above or below the threshold value of the P, we can accept or reject the null hypothesis to check that whether the model is significant or not. This is another important parameter which is introduced for multiple regression. Whenever there are multiple input parameters, only R square is not good enough. So R square have a limitation. That is, if you incorporate multiple input parameters to the model, R square value cannot detect whether the parameter is important to the model or not. It will always increase. You can see the first point, R square never decrease when adding predictors. So if you add predictors, that means the inputs, R square always increases. So that will be a difficult thing to understand, because sometimes the model parameter, suppose if I say crop yield, with the crop yield, how much I have scored in my HS, it is not important to the crop yield. So that means that is a vague parameter, that is an absurd parameter. But if you introduce that also, R square will increase. So we have to have some parameter which will help you that if some input is introduced, if it is not important to the model, R square should be decreased. This is the thing that should maintain. So in copy, if I incorporate my HS marks, the R square should decrease. So it will be done by using the R square adjusted. So if you some parameter is introduced in the model which has no importance to the model at all, R square will definitely decrease. So you will understand which parameter to keep, which parameter to exclude from the model. And the definition, it is only applicable, you can understand, for the multiple regression, because for simple regression, if you put P equal to 1, you see, we have done, this will be n minus 2, I think. So if you put n equal to P equal to 1, so this will be get cancelled. So it will be 1 minus SSC by SST. So R square will be, we will obtain the previous form. So my point is, for multiple regression, R square adjusted will be a significant parameter, which we will use. Another part is, suppose we have a categorical predictor. That means, suppose there is a input parameter which will specify which particular brand of fertilizer we are using. So suppose there are A, B, C, D, 5 brands we are using. So those A, B, C, D parameter, they are not numerically defined, but they are categorically defined. But categorical parameters, they are not like 2.5, 3.6. These kind of values are not there in the categorical parameter. There will be some name of the fertilizer, some name of the pesticide. These kind of things are there. So how to deal with that in the case of regression? We will use something called indicator variable. So indicator variable will do what? Suppose if for it is A, we will use the value 1. For it is B, we will use value 2. So 1, 2, 3, 4, 5, these kind of values we can replace directly in the in the categorical variables. So by replacing the categorical variables with the numerical values, so this is called the encoding procedure. By doing the encoding procedure, we can do the regression. There is another concept which is very important to the regression, that is called multicollinearity. So why this multicollinearity is very important? So multicollinearity is the correlation between the input variables. So please understand that if you have, suppose, say 5 inputs. So suppose the crop yield example, let me take. So you have irrigation, you have the sunlight exposure, you have the pesticide that you are using. So these are all correlated to each other, correct? So the correlation, if it is very large, suppose the irrigation is highly correlated with the pesticides that you are using, or the suppose the fertilizers that you are using. So if the correlation is quite high, the regression model will not be stabilized. You can see this diagram. Suppose you have a cross like this. On this cross, you can put a plain sheet. It will be stable. But if the cross is not like this, if it is like two lines, they are being close, so you cannot balance a sheet there. That means whenever the these lines are very close to each other, you cannot balance a sheet. If it is quite distant to each other, that means the ideal distance is 90 degrees, then you can stable. So our target is the input variables should not be very much correlated. Then the regression model will not be stable and it will not give you the good results. So they should be independent to each other. So we need the multicollinearity to be 0 or at least very less. So how to detect this multicollinearity? There is a term called variance inflation factor, which is also known as VIF. So this VIF is defined by 1 minus 1 by the R square. So if the R square value is quite large, the VIF value will also be large. So VIF value, ideally, if it is very more than 10, we cannot take that. And if it is very less, then we can take. So this VIF value is also another factor to detect the multicollinearity. There is other things that need to be also kept in mind. That is called inflation point and influence point and leverage point. So this influence point and leverage point, these two things should also be kept in mind whenever we are doing some regression. What is this leverage point? A leverage point means some point which is very far away from the model. So these points are very close to each other, but this point you see very far away. So that means this is the outlier, very high value or very low value. So if this point is lying here, is it affecting the model? My answer is no, because if this point is situating over here also, any question is there? Hello? If the point is lying over here also, then still the regression will work because it is lying on the line, so it is not affecting the regression. But suppose this point is not lying here and lying here, this particular point, then it will affect because the line, it will drag it down as it is being indicated by this dotted line. It will drag it down. So for a single point, for a single outlier, if it is not lying on the line, if it is very far away from the line, it is dragging down the line and it is affecting the model. So you can see the model is now becoming bad whenever there is a point that is being taken far away from the points. So this is called leverage point and this is called influential point. So our leverage point may or may not be bad for the model, but an influential point is very bad for the model. So we have to detect that and we have to remove that from the model so that we can have a good fit. So for which we have some statistic, Cook distance and this kind of terms. So I'm not going into that. So there is one simple example that is being given with the OLS regression. You can see what are the interpretation of these coefficients of the regression. If you put x equal to 0, y cap equal to 2.1. So that means if you have predicted value equal to 0, the response value is the intercept of the model. And what is the slope interpretation? So for a unit amount of increase in the irrigation, what is the increment in the crop yield? So if you understand this, you need to have the interpretation of the slope. And R square value you can see here 0.7, which is not very good, but it is still fine for prediction. And the corresponding p-values are also being calculated. I will discuss this more in the hands-on section. And the dose response model I have also taken. So I have just checked that the dose response usually have some saturation model. That means this Emacs model is suggesting that the values will be increasing, and then again it is after a certain dose it is saturated. So this kind of model cannot be done with the linear regression. You have to do the non-linear regressions. Specifically, you have to do the logistic regression, which is this kind of non-linear form itself. My part is not covering this particular thing, so I'm not discussing this, but I will just show you the plot where the nonlinear regression takes over the dose response model. So these are the references I have used, and I will go to the hands-on section. Is there any question you want to ask for this particular thing, or I will directly go to the hands-on item? Okay, I will go to the hands-on directly. So there are 4 codes I have taken. So this is called one software. I hope the screen is visible to all of you. So this particular programming language is called R. So this is a statistical programming language where statistical analysis are being done in a very compact manner because of the packages that are available in our program. So as you can see, we have taken a very basic problem first. The data set we are taking, one is irrigation and one is yield. The irrigation values are being taken by 10, 20, 30. And if you want to have some values defined on a parameter, we have to use the concatenate operator. So I have used the C, and this irrigation and yield, if you run it, so this is the run button. So if you run it, so you can see the values are coming in the right-hand panel. So this is called the environment, where the parameters, whatever you define, come here. If you want to have some analysis on the irrigation and yield, you have to define a data frame. So to define a data frame, this is the code for that. So you have now a data frame. So what is the data frame? You can check if I double click on this, the data frame is coming. So irrigation is this and yield is this. So you have defined that in the R program. So now, if we have a plot, so this plot is basically doing the irrigation with the yield plot, and this is a cross plot. So you can see these kind of points we are getting with the crops with the irrigation. So this particular panel shows you the plot, this right-hand corner plot, right-hand corner portion. As you can see, there is a linear feed that is most suitable for this data. So just doing some basic descriptive statistics, you can understand whether linear regression will be sufficient or some non-linear regression you need to do. So how to do the linear regression? The code is very simple. The code is LM, that is linear model, LM. So this LM will help you to do the linear regression. This one you have to do the Y, and this one you have to put the X. So here our Y is, that is our output is yield, and our input is irrigation. That is yield versus irrigation has been given. So if I just run this, you will not see any output here because we have to do the summary. Then the output of the summary can be seen in the console here. If you just observe carefully, all the information has been given by the programmer. What is the slope and what is the intercept? The values are given here. That means y equal to a plus bx. You have got the value of a and b. What is the error? The error amount is very less, you can see. The corresponding p-value, I was discussing the corresponding p-value and p-value. So whether the parameters are significant to the model or not, we have to do the hypothesis testing. If the p-value is very small, that means we have to reject the null hypothesis, that means the model is significant, and if the p-value is large, then we cannot reject. We have to say that the parameter is not significant. So here both the p-values are very less, in the power of 10 to the power -8. That means we can say that the null hypothesis is rejected. That means both the parameters are statistically significant. And yeah, you can see the corresponding R-square value, that is 0.9966. That is very close to 1. So because the plot is, you can see also, it is quite a linear plot. So the R-square value is bound to be large. Here also the adjusted R-square that I was explaining, it is also been given 0.996. But the values are both same. Why? Because it is only a single input-output parameter model. That is, it is a simple linear equation. So here, adjusted R-square and R-square have the same meaning. That is why the values are same. If I just feed the corresponding regression line as well, you can see how it is fitting in the right panel. Let me go to the second code now. Hands-on 2. This one is I've taken for a dose and response demo data. So again, let me just run it. So Azad, now this thing is done. So how to remove this? So there is a clean button. So I will just clean it so that we can do the new analysis. So if I run it, you will see the data is coming now. So again, we will do the define the data frame. And if we just do the regression model run, if you can check by yourself, the estimated values are given. The corresponding p-value is quite less. That means both the parameters are significant. And the regression parameter values are 0.9987 and 83. So they are changing a bit because of the definition problem. Otherwise, they will be same. And if I just run it corresponding panel, so you will see that. But these two programming I have just explained to you. These two programming I have just explained to you. This one second. Sorry. These two programs I have just explained to you. These two are based on some dummy data. So to show you how we will detect the R-square value, the adjusted R-square value, the corresponding parameter, it is significant or not, and also the slope parameter and the intercept parameter. You will get all the information by the R program. But in real life, we don't have this kind of small data, correct? We have a large amount of data that we need to analyze. So you can, there is an option, if you have a your particular Excel data or CSV data, you can load it directly to the R programming. By this particular feature, you can do some coding also. I will not go into that. I will just explain the easiest process to import the dataset. So import dataset from Excel. So this is the easiest process. We'll just go it. Oh, sorry. So there is a package of read Excel that I need to install. So so after installing that, we can do that. But fortunately, R programming gives you a lot of dataset to analyze. So there is a library, built-in library where a lot of datasets are being given. So I will just discuss from that one. So there is a, first of all, I will discuss the agriculture application. That is, there is a data set that is called AgriDat, agriculture data set. So this particular library, you have to, like in your phone, whenever you are installing some app, you have to go to Play Store and you have to install it. Such like that also, in R programming, everything is not given to you. You have to, whatever you require, you need to install that. So for installing, you have to have this option of packages, where you can go to this install button, and you can write the corresponding package you want to install, and you just click the button install, it will be done. So I've done already, and you have to write this library AgriDat. So it will give you the access to the library AgriDat, and this particular data set have many kind of agricultural data. But with the irrigation, there is a direct application of a data which is called Hanks.Sprinkler. So this Hanks, this particular guy, data analyst, has given this data where the sprinkler that has been installed to the particular land for the irrigation purposes. So the sprinkler will spray the water on designated places. So how much it has been covering the area, based on that, the data is being given. Okay. So if I just run this, and if I check the data set, you can see So which block the corresponding sprinkler is being installed, which row and subplot it is doing, which particular brand it is having or location it is having, how much level of irrigation it is having. So irrigation 1 means we are very close to the sprinkler. Irrigation 6 means we are very far away from the sprinkler. How much yield we are having. So you can see that whenever the irrigation is far away, the yield is correspondingly increasing or decreasing. So so this is the data set. Now this data you cannot do the simple regression. You have to do the multiple regression because there are yield is there. So this is the output. There are multiple inputs that we need to take care of. So for that one, there is a code called head. So for head, we can check how many the head of the data. That means the 5 rows that you can check. So you can see in the console the 5 rows we can check. The structure you can check by running the structure. You will get the brief structure of how many parameters are there, what are the features of that. So there are 7 variables and 108 observations. And again, the code is 11. That's the linear model. Now, suppose if you do the regression with yield and irrigation, it is a simple regression. But there are other parameters as well, correct? So there is a gen parameter. So if I want to use that as the input, what we need to do? I can click a plus. I can just write the name of the parameter, that is gen. And if I run that, so it will be a multiple regression because it is 2 inputs, single output. So, but I don't know how much accuracy we will get. Maybe the accuracy is, accuracy is quite good. So incorporating the gen parameter and irrigation parameter will have the R-square value is 0.71, but the adjusted R-square is 0.70. So without the parameter, what was the value of R-square? Let me check. The value was 7039. So that means there is not significant change when we are incorporating the parameter gen. That means you can keep it to the model. There is no red flag to the parameter as such. But if the R-square value is suppose by incorporating the gen variable, if the adjusted R-square value is becoming suppose say 0.5 or 0.4, you have to remove the parameter because the parameter is very bad for the model. So that is how you will understand which one is important for your model or not. There is some error with the plot. I think I will check that later. But this is one code. Okay. That is all because I have run the gen model. That is. Yeah. Now, if I just run this plot, I think it will work. There is some length issue maybe. Let me discuss the next code that will be better. So this one, as I've discussed, that if I have the accuracy of the model, if you want to check, you have this corresponding p-value. If it is quite large enough, you can reject the particular variable, and if it is less, you can keep it all. And the R-square value will give you how much accuracy we have. Let's go to the another data set which is been given to the R-square repository, that is the DRC data. So DRC data is the dose response data. Yeah, this one, DRC data, dose response data. So this one, if you want to install it, DRC data, you can do it from the GitHub. And if you want it, sometimes if you use the latest version of R, it has the DRC data. Otherwise, you have to install it from the GitHub. So this particular library is having a lot of toxicology data. That means this vinclozonine, this particular drug, it is basically a toxin basically. So if you apply it to the cell, it will reduce the intensity or reduce the amount of radiation that a particular cell is emitting. So using that for a high dose, which have some effect, negative effect on the cell. So this kind of drugs are being given, the data set are given in the DRC data, you can explore on your own. So I'm just discussing this vinclozonine data. So if I just give you the snippet of this, so this is the concentration that is given. So effect is, this is basically a data which is being given in the lumen unit. That means how much luminous the particular cell is, how much radiation or how much light the cell is emitting. So if it is the concentration 0, that means highest light. But if the concentration is increasing, you can see the light amount is decreasing. That means it is having the blockage receptor of this particular drug. So we have to be careful whenever we are applying this particular drug, and you can do some prediction on based on this. Where was the data? 1 second. Yeah. And if I run this code, corresponding, you see, we are using the LM. Actually, this one is used for the, as I was discussing, the categorical variables. If there is some variable which has category, you can see the experiment column, the vincozoline column, experiment column. Here, all the values are correspondingly large numerical. So if we want to one value, you would see repeating 5 times, 6 times. So if I just want to write that this 105009 is repeating 9 times. So how to do that? So by using the factor. So if you use the factor, it will be just counting the number of times it is happening, and it will give you the model. So it is beneficial if you use the categorical variable count in some regression models. And LM is the code again for effect and concentration and experiment regression. So this is the multiple regression, as you can see. Let me just run it. The corresponding value of all the experimental parameters, there are 5 experiments that has been happening. They are being given, and you can see one particular experiment having corresponding p-value is quite large, very large. Actually, there are 2 values, 1, 2. These 2 values. These 2 are quite large. That means if you incorporate these 2 parameters, it will be not helpful if you want to do the multiple regression. That means you have to remove all the data of the experimental 1080821 and 11022. If you remove that, then only you can do the simple regression. Otherwise, you cannot do the linear regression. You have to move to the polynomial regression, multiple regression, these things. So now you can understand why this is important, the hypothesis testing. You can give it a glimpse of whether parameter is important or not. You can see the accuracy is also pretty quite less because these parameters are there. So you have to remove the parameters so that the accuracy can be increased. The accuracy is currently been 0.51, 51%. And HSA square is 0.45, which is quite less. Nevertheless, I have also told you for the dose response model, it is better to always do a logistic regression, to always do a nonlinear regression. A linear regression for dose response sometimes not good for the data. As you can see, if you just do the cross plot also, the data points are having a decreasing trend, but this is a curvilinear trend. So that means you have to do some curve fitting, nonlinear fitting. Preferably the logistic regression will do the work. And if you want to do the prediction, that means suppose for concentration 0.15, how much prediction, how much value of the effect value, how much we can get. So if you want to predict the value, you can just run this predict and you can get the value. So for concentration 0.15, what is the value of the effect? 740.1. So these are so our programming has a built-in functionality like this library, like this LM, so by like this summary, for which you can do the easy code analysis without having much more knowledge of the programming. You can just use in basic features and keywords, which will help you to do the analysis. And you have to be very much cautious about the mathematical things as well, because only this p parameter, p values, the slope intercept values, the corresponding F statistic value also will help you to determine whether the model is working good or not. So these are the 4 hands-on that I have just presented to you, and I hope this session is helpful to you. So thank you for patiently listening to the things that I've just explained, and I'm open to all your questions. Thank you. Thank you.
Thank you so much, sir. Participants, if you have any query, you can ask now. You are unmuted.